So good afternoon, good evening, good morning from wherever you are. Hello and welcome to our today's Arctic Passion webinar, which is actually the last one of the year 2024. Thanks you for joining. Our today's Arctic Passion seminar and dialogue is dedicated to a very special topic. It's the topic of Arctic shipping. Specifically, we are introducing you to another one of our services in Arctic Passion, which is POLARIS, and which is to improve safety for shipping in the polar seas. But before we introduce our distinguished speakers and the framework for this webinar, we would love to hear more from you. So we would like to know who's in the room today. We invite you to write us in the chat, your name, your background, and why you're here with us. So when I say we, I mean Lisa Großfeld and myself. We are your hosts of today, and we are both working for the position of polar educator scientist at the Arctic Institute. And we are working in the Arctic Passion project. And according to our little survey, let's see, 80% have answered the survey, so we're gonna wait a little bit more to get a few more answers in. But from what I see, most of you, currently it's a little bit more than half, are from the early career path in the professional life. We have 20% senior career professionals and another 20% in between. And most of you, it's currently 65%, are from the natural science background. And we have a few, about 80% from industry and economy, 12% from social sciences, and 6% from the sector of health and environment. Nice. And actually, yeah, most of you are working in the area. There's no one currently living in the Arctic. And 90% are not living or originating or working in the Arctic. I think I'm gonna leave it a little bit more open, a few more seconds, so you can still post your answers in the survey, and then I will close it and you will see the results yourselves. All right, great to have you all on board. A few housekeeping notes before we get started. We would love to see you and warmly invite you to switch on your camera. At the same time, Arctic Passion has many friends overseas and in many time zones. So for those who are not present, we are recording the webinar, and so please be aware of that as well. The recording will be available through the Arctic Passion and APEX websites. We are welcoming any questions you may have and invite you to use the chat, or especially in the second half of the webinar, get actively involved by raising your hand and speak up yourself. Please mute yourself when you're not speaking. And finally, a few words about your host of today. This online seminar and dialogue is brought to you by APEX, the Association of Polar Educator Scientists. So what is APEX? It's a network of almost 5,500 people interested in polar and alpine regions from all kinds of disciplines and cultural and national backgrounds. The network from early career scientists for early career scientists, and basically a platform for exchange on various topics, maybe knowledge transfer, alternative career paths, or just the celebration of polar and alpine research and regions. Education and training is a very integral part, and as such, APEX was and is involved in various EU projects, of which Arctic Passion is one of them.
So in the Arctic Passion project, APEX is organizing this online seminar and dialogue series and use this as a tool to communicate the results and topics of our project, but also to have a platform for exchange and inclusive and proactive dialogue with a various group of audiences coming from different career levels and backgrounds, and just to share ideas and give feedback to our progress. And what is Arctic Passion in general? So the project is about working on an improved network of environmental observing systems in the Arctic. And to achieve this, we are working together with Arctic communities, with scientific networks, and also decision makers. And more concretely, we are working towards a more better coordination of observing systems. We also help to improve current systems, and we develop new services. And today we are presenting one of these services, and the topic is Arctic shipping, and it's an operational service to better quantify the risk to a vessel as it navigates through ice-covered waters. And with this, I'd like to warmly welcome Andrew Fleming, Zhang, Xinfang, and Sierra Beecher, who are working together with a few others on developing this service for improved Arctic shipping. Andrew Fleming is located in the UK and is a head of the Mapping and Geographic Information Center at the British Antarctic Survey. Xinfang Huang is located in Finland, working as a doctoral researcher at the Finnish Meteorological Institute. And Sierra Beecher is in Canada, working as a researcher as a data scientist at the University of Ottawa. So again, a warm welcome to you. And we are very much looking forward to hear about your work and how shipping can be more safe. And after your presentations, we'll open up the floor so everyone can ask questions and engage on a group discussion. So happy to have you all here, and I'd like to hand over to Andrew.
Thank you very much. Let me just share screen and go to presentation mode. And I hope that that looks as it should. That looks good. Thank you, Lisa. Okay. So welcome everybody, and thank you very much for joining us online today for this webinar about the Arctic Passion shipping pilot service. We're going to do this in 3 parts. I'm going to provide some context and setting information about the motivations behind the service development and what work we've been doing. And then I'm going to hand over to my 2 colleagues who are going to provide you with a bit more detail on some core strands of that work. So, as Lisa pointed out, we are one of 8 pilot services that are being developed as part of the Arctic Passion project. And it's not just the 3 of us around this webinar that are responsible for the shipping service. There's a small cast that are listed there who are contributing to this from various parts of the consortium. But our main focus is on reducing risk to Arctic shipping and trying to improve the information that is available to maritime operators who are working in and around sea ice. So to kind of give some context for what we're talking about here, it's ships that are working in a region where they may well encounter sea ice and icebergs, but they are concerned about this from the point of view of safety, but then also from the point of view of efficiency. Safety is clearly an issue where we've got frozen water on the ocean surface that poses a hazard in terms of damage to a vessel, sometimes damage that can be significant, and accidents like that are to be avoided, obviously. So good information about the sea ice conditions that the ship is operating in is absolutely vital. And the other aspect, of course, is efficiency, and time spent operating and navigating through sea ice tends to be incur a larger fuel burn. So rather than spending unnecessary time, making sure that you've got the right information to make good routing decisions is also critical in terms of proper operations in such a hazardous environment. And mentioning environment, I suppose the other strand of this is trying to reduce the impact on the Arctic environment overall. So a reduction in the risk of accidents, a reduction in the ship time where possible, and fuel burn in the environment is also a key part of and motivation behind providing good information directly to ships. So in effect, we're trying to take ships, and to highlight, this is obviously one of Bass's, well, it's not obviously one of Bass's ships, but it's a ship operating through sea ice, taken from above a couple of years ago. So that's the topic, and it clearly remains a high-profile topic. I mean, a quick look at recent news articles will indicate that there's still an ongoing high level of awareness about the issue of changing Arctic sea ice conditions and how that affects the level of shipping. And it's a common narrative, I suppose, over the last few years to imply that a reduction in Arctic sea ice cover will lead to some increase in shipping activity in the region. Of course, it's much more nuanced than that. Some of the recent articles highlighted here indicate that yes, there may be a reduction, but it's also about the changing types of sea ice that are experienced and how that's changing shipping patterns. So it's as ever, it's a much more complicated picture than just a simple story of less ice equals more shipping. And of course, not only have we got that, but it's a complicated geopolitical arena as well. And so there's a lot of ongoing attention to this activity and an awareness of the need for good information and best practice to be followed to ensure that ships are operating as safely and as efficiently as possible. We have good information historically that about the patterns of the changing patterns of ship activity. And these two graphics are taken from the Arctic Council PAIM Arctic Traffic Ship Database and shows a change in ship activity over the period between 2013 and 2019. So you can see there's obviously, as we've just referred to it, a change in the level of shipping activity. But again, this doesn't show very clearly how that applies to at a detailed level of how are these ships operating and interacting with sea ice. What sort of risk does that pose to the vessels? What type of vessels are operating and at what times of year, for example? So there's a lot of detail behind just a straightforward picture of a changing volume of shipping traffic. So we have good information about the patterns. But in terms of judging what the risk is to a vessel from sea ice, then there is now an established methodology for judging that called the POLARIS system. So you may be aware that a few years ago, the International Maritime Organization introduced the Polar Code, which introduced a range of regulations, guidelines on how ships should be operating in both polar regions. As part of that, they mandated a system that meant a ship should be able to judge its limits of operations in sea ice, i.e., it should be able to say, for these sea ice conditions, is my vessel within its operational limits or operating in a higher risk area beyond the limits of my particular vessel. And so this POLARIS methodology was developed, and it effectively is relatively straightforward on the surface of it. So on the left-hand side, it takes into account the sea ice conditions. That's a combination of the sea ice concentration, how much sea ice there is on the surface, and then what type of ice it is. Is it relatively young, thin ice, or is it much older and thicker ice? And that type of ice is effectively a proxy for how strong the ice is. So you take a combination of those sea ice conditions, which you might take from an ice chart produced by one of the National Ice Services, the example on the left-hand side here, which shows the ice regime, i.e. the different mixture of the different types and concentrations of ice. And then it combines that with a risk index value for each type of sea ice. So for each type of sea ice included in that regime, what's the risk value for that? And for the first time, this risk assessment system takes into account the type of vessel, i.e. how strong the vessel is, taken as its polar class, which is a way of denoting how strong a vessel is. PC1 is a very strong ice-capable icebreaker, effectively, going down to PC7 and the 1A, 1B, 1C values below, which are less strong values. So a combination of those sea ice conditions, these risk values, then results in a score, which is known as a RIO score, Risk Outcome Index, which neatly translates into a traffic light system. So if it's green, it's a positive RIO score, then normal operations, you're within your limits. If it goes into negative values, then you're either operating with elevated or higher risk. So this is the methodology that we've used for assessing what risk level a particular vessel that we have databases been operating at. It's worth pointing out, and I think it's worth acknowledging, that there are still limitations within the Polaris methodology. We know from other work that's taken place within the International Ice Charting Working Group that uptake of Polaris is relatively low as it stands, for reasons such as the limitations, such as the lack of access to higher resolution information about the sea ice conditions. I mean, you can look out the window of your bridge and judge the sea ice conditions, but it doesn't give you a view over a very long distance. It's a much limited one. Equally, the Polaris method currently at the moment doesn't take into account important parameters such as icebergs and ice pressure or ridging within the sea ice. And if you are using ice charts, then there's a timeliness issue in that ice charts are issued and then they may not be updated for a number of days, and so it gets out of date. So acknowledging that there are limitations to this method, but that's the established process that we can use. And now my slide's not advancing. It is now. Okay. So the pilot service is really trying to do a number of things, and I've broken them down here. Firstly, we've taken a look at this historical pattern of shipping activity, and Sierra will follow on from this presentation with a much more detailed view of that work of taking a number of years worth of shipping activity, marrying it with a number of years of sea ice information, and unpicking what the particular patterns of activity and behavior are. So that's an important thing in terms of judging and understanding what historical patterns of activity have been, but also as an indication of how useful this sort of information is in terms of assessing what shipping routes are viable, have been viable in the past, or may be changing. What sort of ice conditions and risk might be encountered as a way of judging what polar class vessel is required along particular routes or are possible for particular routes. So there's a whole range of planning information that can be extracted from that. The other strands of the pilot service that we've been working at is proving the delivery of this information to vessels based on their current location. And we've been working with a ship's AIS data, and particularly positions picked up from satellite AIS data, that gives a position and allows delivery of tailored information to that vessel. And then the other strand that Xinfang will move on and present is the really a novel approach of taking sea ice information from different sources, from forecasts. And so instead of saying, this is the Polaris risk assessment at this particular time, or rather based on the sea ice information that may now be a few days old, is to understand what the options and value of forecasting that risk information are. So Xinfang will come on to that as well. Sorry, and this is a quick snapshot of this historical work that I said that Sierra will move on to. She'll provide much more detail on this, but you can see it's covered quite a comprehensive number of vessels, and then the Polaris forecasts that Xinfang at FMI have been producing. I'll leave them to provide much more detail on that. The last thing I'd say, just in terms of the other strand of delivery and testing this, is that none of this is useful unless we prove that it's worthwhile operationally, and we get feedback from vessels. So we have been working on demonstrating the service in terms of taking the forecast, taking the information that's the forecast of Polaris information, and then delivering it directly to the ships based on their location. So we've done this in a number of instances, highlighting just a couple of them. We've got the US Coast Guard vessel Healy during a demonstration last summer that was operating in the Arctic, and you can see its ship track there on the right-hand side. And then more recently, we also worked with the Danish Royal Navy vessel Triton off the coast of Greenland to do a similar thing. So taking those risk assessments, you can see the traffic light colored graphic there, and marrying that with their current position in order to deliver it and get feedback from them. And that's been a really useful exercise and something that we plan to do more on in the remaining few months of the project. Right, with that, I'm going to pause there and hand over to Sierra. But just before I do, I'm aware that we're going to come back to the second part of the webinar, and there's an opportunity for questions. If I was to prompt you to think about one thing, and one thing I'd be interested in understanding from you is what level of awareness you have of the Polaris risk assessment system and its uptake and any of the limitations. I think that's something that we found that there's quite varied understanding of. So if you have any direct experience of this or link with operations, then I'd be really interested in that. Right, with that, I'll stop sharing and I'll hand over to Sierra.
Hello, everyone. I'm excited to share insights from the historical risk analysis we conducted as part of Pilot Service 6. So climate change has dramatically reduced the extent and thickness of Arctic sea ice, which in turn has opened up longer ice-free seasons and new opportunities for Arctic shipping. But as we'll discuss today, less sea ice does not necessarily mean safer navigation. And to understand the risk involved, we turn to Polaris, which helps to assess ice-related risks and for vessels operating in the region. So for the scientific exercise, we acquired Automatic Identification System, or AIS data, from Exact Earth and the Arctic Ship Traffic Database. And this provided us with a detailed spatial record for more than 45,000 ships operating in the Arctic from 2012 to 2022. And then this data was cleaned and decimated to daily positions. We enriched the ship position data by adding key attributes. And these key attributes were ship type and ice class. The ice class indicates the ship's hull strength and its ability to navigate through ice, which is crucial for assessing risk in ice-infested waters. And here's an example of the data we collected for a vessel. To determine the operational risks to the vessels, we integrated sea ice data from weekly US national ice charts. And then using the risk index outcome equation, we multiplied the concentration of sea ice along with the risk index values, which is based on the ice class and the ice condition encountered. A positive risk index outcome value indicates normal operating conditions, while a negative value indicates increased risk, and that's split into two categories, elevated and high risk. We were able to assign risk index outcome values to over 288,765 ship position reports between 2015 and 2022. And here you can see RIO thresholds for 3 different ice classes from their RIO values on the Polaris chart. So this map highlights the distribution of ship positions in ice-infested waters versus open water. It represents 64% of the analyzed positions and 2,269 unique ships. So from that, pulling out the open water, all of it was normal operation with normal operating conditions, and that's 81% of the data was in open water. However, 19% of the ship positions were in ice-infested waters where risks varied. So from that, 5% of the ship positions were classified as high risk, and that involved 452 unique ships. 8% were categorized as elevated risk, involving 437 unique ships, and the remaining 87% of positions were in areas deemed normal for operation. The normal operation category experienced significant growth over time, especially from 2018 to 2021, where there was an impressive 229% increase. So shipping is increasing, but it's good to see that a lot of it is normal operating. Over time, there was a decline in the percentage of high-risk ship positions in ice-infested waters. For example, high-risk operations decreased from 12% in 2015 to a low of 3% in 2020, before slightly increasing to 5% in 2022. Over time, the proportion of elevated risk positions also declined from a peak of 18% in 2016 to just 3% in 2020, with a slight rebound to 6% in 2022. The slight increases in recent years highlight the continued need for careful monitoring and the adaptive risk management as Arctic shipping evolves. So here's an overview of the number of unique vessels in ice-infested waters, broken down by their vessel type as well as their ice class. So fishing vessels were the largest category overall, with significant representation in polar category C. And polar category C includes all polar classes weaker than a 1A super. Cargo ships and tankers dominated polar category B, which is PC6 and PC7, so mid-strengthening. And then government and research vessels were well distributed across all ice classes, including rare categories like PC1, 2, and 3, which are very high strengthening. The fishing vessels dominated the high-risk category, particularly in ice classes 1A super with 16% and 1A with 14%. And cargo ships were the second largest contributors with 13% of high-risk records in PC7. Tankers dominated the elevated risk category, with ice class PC6 representing 31%, and cargo ships were the second largest contributors with 21% of elevated risk and records in PC6. So again, looking at the limitations, while the historical analysis provides valuable insights to Arctic shipping, it's important to acknowledge the limitations inherent in the data and the methodology that we used. So the first limitation is spatial data inaccuracies. So the Arctic Ship Traffic Database, ASTD, includes errors such as AIS vessels moving their locations or appearing in impossible locations like on land or within permanent ice. Additionally, positional inaccuracies are present, such as latitude and longitude reported to just one decimal place, or sometimes as integers. The next limitation is that the National Ice Center charts are low resolution in some areas with large polygons that lack detail, and that's due to manual digitization. A significant limitation is the mismatch between ship position data, which is recorded daily, and ice charts that are weekly. So this creates uncertainty when overlaying ship locations onto ice conditions, as the ice chart may not reflect the exact conditions on the ship's travel day. Assigning correct vessel ice classes is another challenge. So ships may register their ice class inconsistently across systems, or the conversions to polar class categories may be inaccurate. For example, research icebreakers can sometimes be misclassified as low ice strength vessels, impacting their risk index outcomes. And then finally, the exclusion of icebergs is a limitation, as it's critical for ship operators to know where they are, and it's not accounted for in the National Ice Center charts. But despite the limitations, the study provides a valuable framework for assessing risk in Arctic shipping. And these insights can inform safer navigation, adaptive planning, and targeted policy development as the Arctic continues to open up to global shipping. And with that, I'll pass it to Xinfang.
Yeah. Yeah. We have been talking about risk index outcome quite a lot in ICEChart or from satellite data. But it's also very important to look at the model forecasted risk and its outcome, because we have to have navigation tactics for the future. So we need to plan in advance. Like we need to look at how Rio is distributed based on the modeling data that we get. So good afternoon, everyone. My name is Xinfang, and I'm from FMI, and I work in the Marine Research Unit. I would like to introduce how me and my colleagues we use the novel algorithm method to derive sea ice navigation risk forecast from the model forecast based on POLARIS. I will first introduce how Rio is calculated based on modeling sea ice data using different methods. And since we want to have visionary tactics on the current and future maritime operation, that's why we have to rely on the model forecast of sea ice conditions. But models, they have strengths and limitations. For example, this model might be good in like the warm season, but it's not good in the cold season. This model might be good in specific regions, but are bad in the other regions. So we have to evaluate the model forecast capabilities for risk and X outcome. And it is very important for mitigating sea ice hazard when we make operations, especially when we are making plans like in advance of navigation. Okay, so risk and X outcome have been introduced for 2 times, but I would like to supply something. Since like I'm using modeling data to calculate risk index outcome, and as you can see, there's n terms in this formula, and in some modeling data, it is multi-ice category models. It might have 5 ice categories, so n is the ice category number. So if we have 5, then n equals to 5. If it is a single ice category model, for example, Copernicus or ECMWF modeling forecast, they are all single ice category model, then there's only this first term of this formula. So here's an example of how risk index outcome is distributed in Arctic. And Andrew has already introduced the color code, so I don't repeat here. So we did some small adaptations on the previous approach to calculate risk index outcome. So previously, we only used sea ice thickness and sea ice concentration to calculate risk index outcome. But now we have the like novel method is that we determine the polarized ice type based on all kind of available sea ice data. Of course, first of all, we have to have a sea ice concentration since it is the first term of the formula. Then we have to at least have the sea ice thickness to determine the ice type. But then salinity and ice age are the bonus points that we included in the novel calculation method to better determine the ice types. And they matters, especially when sea ice is thicker than 120 centimeters. So here we have 3 methods to define the polarized ice type. The first one is to only use sea ice thickness. Of course, here's some limitations for thick ice, since if we use this method, we don't have other kind of salinity or ice age conditions, so it might be inaccurate. But if we use the second and third method, we can determine the polarized ice type much better based on the ice information that we have. So then, of course, we need to have a ship class. Then with these 2 information that we get, ice type and ship class, then we got a value, risk index value. So I would like to give an example of how to calculate risk index outcome. For example, we are given an ice concentration, which is 60%, but in this formula, we have to put it in tens. So if it is 60% concentration, then it's 6. And if we use the one of the previous 3 methods to determine that, okay, it is the second year ice, and then we have the ship class of PC5. So now we know that the risk index value is this cross-section -1. And we use 6 times -1, then we have -6, which is the risk index outcome. And since it is minus, so the color code for it is red, then we can easily figure out that, okay, it is a no-go zone. Could someone please put this link into the chat? So here's the link of the GitHub page of the real calculation code. It is co-developed by me and my colleague Andrea Gihesh from DMI. And this code can apply to all kind of sea ice data. Well, I'm applying it on sea ice modeling data, but other people, they are like free to apply it on satellite data or even on ice chart. If it has the ice condition parameters, at least it should have sea ice concentration and sea ice thickness. Then we can use this code to do the calculation. And here, these 9 figures are the transpolar route real profile for 3 different PCs and 3 different modeling data sources. So why do we focus on transpolar routes? Because based on like previous analysis, the transpolar route might be opened up in 2050. And like in my study, I defined the transpolar route, as you can see in the upper right corner, to be plus minus 5 degrees average around the 0 degree longitude and 180 degree longitude. And the latitude range is from like 70 degree north to the North Pole, and then back to 70 degree north on the other side. Then these become the x-axis. So you can see 7, 90, and 70. And then on the y-axis is the mosaic expedition period that we are focusing on in this current study. Because in a future study, we want to use mosaic data as a reference. So there are 3 modeling data sources that we used. They are DMI high concise hindcast, Copernicus forecast, and ECMWF subseasonal to seasonal forecast. If we see like PC2 and PC7 profiles, we can see that different models, they make really good agreements. It is because models have a good agreement on where is the ice edge. But like in PC5, real forecast is quite different in different model result, because models have a lot of variations in ice covered zone and in different time period. But anyway, they have an agreement that the most risky time to go over transpolar route is between February and June. Well, the model have the most disagreements on time and spatial range on the no-go zone distribution. And we have checked that behind this red zone and the yellow zone, the sea ice concentration is almost like 100%. So what is the other crucial parameter which is influencing the risk index outcome result? Then it is the sea ice thickness. So it's a bit hard to validate risk index outcome like model forecast, because there's only very few available real in the ice chart, and it's hard to make the validation directly. So we were thinking of validating the modeled sea ice thickness instead of validating real. So, okay, here, so we compare the three modeled thickness against the cryoset 2 observing data set. And this thickness data source is from Jack Landy, and he has generated sea ice thickness during the Arctic melting period. Well, the scatter plot and the linear fit line demonstrate that the correlation between the modeled and the observed sea ice thickness. We can see that the DMI model simulates the thickest sea ice thickness, and ECMWF is in the middle, and the Copernicus model simulates the thinnest sea ice thickness. And from the clusters and from the linear fit line, we can also see that all of these three models, they have a tendency to overestimate the thin ice, but underestimate the thick ice thickness. I wanted to further prove it, so I also have another plot which is only focusing on the thinner ice under 2 meters, and the linear fit line become closer to y equals to x, this line. So it further proved our result. Since I previously mentioned that we have 3 real calculation methods, one is the basic method, and the other 2 methods are using salinity and ice age. So I want to compare 3 of them. So here I compare 3 of them by comparing the no-go zone length in the Mosaic expedition period. For DMI data, we used all these 3 methods. We can see that so the top one is PC7, the middle 3 is PC5, and the bottom one is PC2, because it has thickness, it has salinity, it has age. So it gave us possibility to compare these 3 methods. But in Copernicus data, it only has the thickness parameter and the age parameter. So we only have these 2 methods. And in ECMWF data, since there's only sea ice thickness and sea ice concentration available, so we only used 1 method. So from these 3 plots, we can make conclusions about the general trend of the no-go zone length across these 3 PCs. And so in PC2, which is the bottom line, in all these 3 figures, the transpolar route remains navigable, that the no-go zone length is 0 all the time. And for PC7, which is the top group of all these 3 figures, so for the whole time period, the transpolar route is not navigable. And it exhibits a strong seasonal variability. For example, the maximum is observed mainly in March and April, and the minimum of the no-go zone length is in September. And there's also inter-method variability, that different methods are simulating different lengths of the no-go zone, especially during the warm season. And for PC5, so the group in the middle, if you see the box, we can see that especially around April, there's very significant difference among different methods, despite they are all forecast for PC5. So the key difference across the method is that the basic method, where we only use sea ice thickness, indicate the much shorter no-go zones, especially in the warm season. It suggests there's a better navigability, but if we include the ice age and ice salinity method, it shows slightly longer no-go zone, means that it's more dangerous, which is predicted by these 2 methods. like the age method and the salinity method also have some difference depending on the sea ice condition. Like in most of the time, they are quite identical, like for PC7 at least, but for PC5, it's still quite different. So now we have an overview of how is the model performance and what is the difference between different real calculation methods. And first, the model have good simulation on ice edge based on what we see in PC2 and PC7 profile. And then DMI data is being quite conservative. It means that it's overestimating the risk for navigation in sea ice. And Copernicus model might overlook the potential risk in ice. And ECMWF model is in the middle. And all of the models, they tend to overestimate thin ice thickness and underestimate thick ice thickness. And this novel method of including ice salinity and ice age help us to figure out the more potential risk that we couldn't see when only using the basic method. So it's a good idea to apply this salinity method and age method if possible, especially for the thick ice, since models have the disadvantage of underestimating the thick ice, which is underestimating the risk. So what is the next step? I'm waiting for the second run of DD climate modeling data simulation. And we are going to do the same statistic and compare with the current statistic from these 3 different model data sources. That's all for my presentation. Thanks.
Great. Thank you all so much for sharing your work and also hearing about your service, which is really relevant. So now it's time to exchange and to raise questions or feedback. You can do it in the chat or just raise your hand and then speak up. We already have one question in the chat from Sarah Fleury. She asks, how do you know about sea ice thickness, age, and salinity? From models or observations?
For models, then we have like some models, they just have 3 ice parameters that we can, for example, for DMI data, I just directly ask my colleague, could you please run the model for me? And I get these 3 parameters, then I got it. And for example, for Copernicus data, I fetched sea ice age and sea ice concentration directly from their FTP server. Then I just put them into real calculations. So it depends on what you have, but at least you should have thickness and have ice concentration. If we don't have any of these in model parameters, then of course, no calculation of real can be conducted.
And we don't have observations from satellite for many of those parameters. Concentration, yes, but any thickness measurement is too infrequent to be of use here.
Okay. And you said that you're working with ship operators and ice services. And how do you see the service will be more used frequently? And how do you get in touch, or how do they get to know about the service?
So addressing the first part of that, initially in terms of what's required really in working with the ice services, I think the major limitation that we've picked up from feedback is the resolution, and that's both spatial resolution and the temporal resolution. If we're reliant on ice charts for the source of the sea ice information, then concentration and stage of development, then at the moment ice charts are relatively low resolution, and for most areas relatively infrequently produced. So there's a move here that allows the forecast to address that to a certain extent, but again, spatial resolution is the major issue. There are a number of developments within the ice services and the wider research community on improving automatic classification of sea ice to give much better information, which seems to be the best route or signpost to the necessary information to develop a much higher resolution and more timely risk product, and might allow other parameters to be built into it as well. In terms of access, you mentioned working with the ice services. I think working with the International Ice Charting Working Group, which is the forum within which the ice services collaborate and discuss research topics, that still remains the route of choice in terms of authoritative sea ice information. And I would hope that in time this sort of information gets folded into the outputs of the sea ice information services, the formal sea ice information services in the future.
Thank you, Andrew. Before we take Michael's raised hand, I would like to read out Sarah's second question, because I think it's kind of connected to her first question, which is on salinity and why this is an important information. It's salinity of the ocean on the leads, question mark.
Shall I answer that salinity question?
Sure.
Can I share my screen again?
Of course.
Yeah. So if we are talking about the salinity, we can have a closer look at these charts. So this is kind of visualization of my code. So see here, if you like have a sea ice thickness, for example, 180, if you have less saline condition, then it is categorized to like thick first year ice, means like a weaker ice type. But under a same ice thickness condition, but you have higher salinity, then we categorize it to kind of a stronger ice category, means that there's more risk. So if we add the salinity into our algorithm, then we can know that we should get a lower risk index outcome value. So that's why salinity is included.
Thank you. Thumbs up from Sarah.
Thank you.
Thank you. Okay, Michael, it's your turn.
Yeah, thanks a lot. Thank you, everyone, for these interesting and very relevant presentations on the service. I was just wondering, thinking about the future aspects or the potential future developments which you just mentioned, Andrew. I mean, I do know that there are a few developments on the way using AI, artificial intelligence, to improve downscaling or improve, for example, the categorization of sea ice based on current altimeter data and so on. So I was just wondering, where do you see the biggest, let's say, the lowest hanging fruit maybe in making a big step forward in the risk assessment for short-term forecasting? Is it really the improved resolution, or is it the additional information on ice thickness or ice type coming from different sources combined with AI maybe? Or maybe it is more information on ridge distribution. or overall sea ice pressure, large-scale sea ice pressure, things like that. Any idea what could be the most impactful one?
Well, I mean, my pet topic almost is the sea ice pressure one. I think that's the most impactful one from a navigation point of view. I mean, ultimately, and I could kind of point back a couple of weeks to our own ship captain and what they were faced with, and the biggest uncertainty was not whether there was ice or not, or what type it was. It was the pressure factor. So I think that's absolutely something that might need to that would make a big difference in terms of a revision of how Polaris is done. So I think everything you referred to under the broad AI label points in the same direction. Really, it's not necessarily a trade-off of resolution versus which parameter. As I said, there are multiple approaches here whereby we get improvements in the understanding of the information about the sea ice type and concentration, but primarily the type, which is the missing factor. So, but that's a proxy for strength, which is so that's the, if you like, the low-hanging fruit. Is the bit about the resistance that we don't have good information on at the moment. So I think that's where it points to at the moment.
Yeah, thanks, Andrew.
We have another question in the chat from Stephen Heel. He's asking, I'd be interested to hear if you or others have considered additional risk parameters, such as the distance from search and rescue and closeness to environmental important sites.
Certainly, the Polaris system does not quantify those, or does not use those as factors to change the risk outcome. So you could be right next door to a search and rescue facility and in the middle of an environmentally protected area, and it wouldn't change the outcome of the Polaris score. It's based purely on the sea ice types. I think it's fair to say that all ships are considering a wide range of sea ice, weather, environmental information when they're planning their operations, and all of those factors get folded into that, of course. But in terms of a formal quantification, not yet. But that's a good question about some unification of risk assessment of a particular voyage plan that would account for all of that. It might be a question about how to unravel that in terms of which parameters are of more importance to which ships. But yeah, interesting question.
Awesome, thank you. I think we're gonna ask or let Björn ask this question, and I'm gonna read it. And while reading it, you may also want to add on. Do you see that as important to improve on mechanical thickness with redistribution, like rafting, ridging, and openings in the modeling, improving the risk assessment?
I think that partly comes back to the point about the pressure within the sea ice field. That parameter and ridging is not factored in, and it's seen as one of the key parts of the risk assessment that's not factored in at the moment and included. And it's probably worth highlighting one of the misconceptions of Polaris sometimes, that the system is not there to determine navigability. It's about risk to the vessel of a particular polar class. So you might be within a region that's entirely within the ship's capabilities, but it's still unnavigable, i.e. they can't make progress for various reasons. So yeah, absolutely. I think the thickness is and type, or however you want to refer to it, and then that pressure element and the ridging element is the key bit that we're missing some way of better quantification to fold into a revision of this system. I hope that answers your question, Bjorn. If not, come back to me.
Okay, sounds good. Yeah, we have one last question from the chat, quick one. Is the deliverable or paper about historical analysis of shipping activity publicly available?
Over to Sierra.
It isn't as of yet, but it will be very soon. But we do have the data in a story map. And I believe Andrew does have a slide with the QR code to our story map where you can interact with our data and see some of our graphs.
Yeah, let me share quickly, and I can put a QR code up. There you go. And if I scan down, right, so you should be able to see that QR code. That will take you to, and we can make this available afterwards as well, or I'll put it into the chat. But that will take you to an Esri online web story map, which has some additional information on what we've been doing. It doesn't yet contain all of the historical information results that Sierra pointed to, but it will do. We'll update that. We'll update that soon. In terms of a publication, that's absolutely part of the plans. Now that the historical analysis is complete, we need to write that up, and that's underway. So there will be more than one publication coming out of this in the near future that Ottawa are leading along with the rest of us. That we're when is soon, and we're planning on it being first quarter of next year.
Awesome, thank you. Yeah, I think we are hitting the hour here, so we're slowly closing this event. I'm gonna post the last message here for you. So actually, yeah, we're coming to the end of this online seminar and dialogue. Andrew, Xinfang, and Sierra, thank you so much, all your contributing colleagues, of course, for presenting your work today and your passion in our project. It was a pleasure to listen to you, and to your audience also. Thank you for your time and your contributions. See you hopefully soon again in one of our next Arctic Passion online seminars. The next one coming up is on the topic of wildfires and the risk management of fires. Will take place in February, so keep your eyes open for that announcement. And well, once again, thank you for joining us today. Have a great rest of your day, and see you on some next occasion, hopefully.
Yeah, many thanks everyone. Bye bye.
Goodbye.
Thank you. Bye bye.
Thank you. Bye bye.